Hey guys, in this video we're going to be looking over chemical equations and reaction types. In here we're going to be balancing chemical equations and predicting the products of simple combustion, decomposition, and combination reactions. So let's start out with the idea of stoichiometry, as this is what this is kind of all leading into. So a lot of this unit is going to be revolving around stoichiometry, so we're going to be building up to this. So let's look at what this means. So we have stoichion, which means elements, and we have metron, which means measure or to measure. So we're going to be measuring elements within stoichiometry. So stoichiometry itself is going to be the calculation of amount of reactants and products in a chemical equation or chemical reaction. So it's all based on the conservation of mass. So the conservation of mass, or law of conservation of mass, states that mass or matter is neither created nor destroyed during a chemical equation or during a chemical reaction. Okay, so when we think about a chemical reaction, whatever is on our reactant side, it's going to be the same as on our product side. So our matter on both reactant and product side will be the same. So we're not changing how much mass or matter we have, we're just changing its form. So mass or matter is not removed or gained, just transformed. Okay, and this is first stated by this guy right here, French scientist, Antoine Lavoisier. Okay, so let's look at what I mean by a chemical equation. Right here I've got some molecules. Specifically I have CH4, oxygen, carbon dioxide, CO2, and water, H2O. These are all chemicals. These are all compounds or molecules, and they are going to react together. The things on the left side are going to react to produce the things on the right side of this chemical equation. So what we see is that our CH4 or methane is going to combine with O2 to produce carbon dioxide, CO2, and water, H2O. So this is how we write a chemical equation right here. CH4 plus O2 goes to CO2 plus H2O. Everything on the left side is called a reactant. The things on the right side are called products. Reactants and products. The arrow that I drew means to yield. And then any positive on the left side means reacts with. And then the positives on the right side are just an addition of the products. Two or more products are indicated by having that plus sign. Okay? Now, CH4, O2, CO2, and H2O are specific compounds. And we know that from previous units where we talked about if we have a compound, it has to have a set ratio of our different atoms within there. So to have CH4 or methane, we have to have one carbon and 4 hydrogens. To have an O2 molecule, there has to be 2 oxygens. To have carbon dioxide, it has to be carbon and 2 oxygens. And then to have water, it has to be 2 hydrogens with 1 oxygen. So these subscripts that we see down here describe how many of that atom we have within that compound or molecule. So those are things we can never change. So when we're thinking about conserving matter or mass, we have to make it so everything on the left side matches everything on the right side, but we do this not by changing those subscripts, we do it by adding something called a coefficient. So to keep with the law of conservation of matter, we add coefficients to balance each of the atoms. So at the end, no atoms are going to be destroyed or created. There's going to be the same number of each atom on both sides of our reaction, our reactant side and our product side. And this is what we call balancing equations. So balancing equations is, again, due to the law of conservation of mass, and it's so that we keep the number of atoms on our left side the same as the atoms on our right side. So the sum of each of the atoms should be equivalent on both sides of the chemical equation. Okay, so we add these coefficients to balance out our molecules and compounds. We never ever change subscripts because that changes the compound. So add coefficients to balance. Never change subscripts. The thing that's going to be included in our chemical equation a lot of times are reaction conditions, where reaction conditions are the environmental conditions under which the reaction takes place. So these are going to be placed above the arrow or shown above the arrow. So for instance, we might see something like this, where we have a delta. This means that heat is applied. So we've heated the reaction. Or we might see this right here. This means that light was introduced. So these things are required for the reaction to take place, or this is the optimal condition for the reaction to take place. Another thing that's often shown is physical states of the reactants and products. So these are going to include solids, which is going to be shown as an S in parentheses, liquids, shown as an L in parentheses, gases, shown as a G in parentheses, and aqueous, which means dissolved in water, shown as an AQ. And they'll be shown by whatever molecule or compound that they're describing the state of. let's look at the steps for balancing equations. The very first thing you're going to want to do is write the chemical equation if it has not already been done for you. A lot of times you'll be given a word problem instead of an actual chemical equation, so you need to convert that word problem into the chemical equation using the names to go to chemical symbols. And then after that, you're going to, underneath your chemical equation, list the elements present on both sides of your reactant and product under the respective sides, making sure they stay in the same order on both sides. Then you're going to total out how many atoms of each you have on your reactant side, then your product side, and you'll write those totals underneath the respective sides. After that, you're going to start adding coefficients in front of reactants and products to try and get the atoms the same number on each side. So you want however many atoms of one type the same on your reactant side as on your product side. So you add those coefficients in order to do that. The way in which we balance is this order. First, we do metals. So any metals we see are going to be balanced first. Then we're going to next we balance polyatomics. Okay. After that, we're going to balance non-metals except oxygen, hydrogen. Then we're going to balance oxygen. And lastly, hydrogen. And generally what you do is you go down this list, and if you end up unbalancing something that's above, you go back to that thing above. So if we balance out our metals and then we balance out our polyatomics, and that will unbalance our metals, we'll go back up to metals, and we'll keep doing that until we get everything balanced out. Make sure when you're doing this that you adjust the totals to reflect the changes that you made as you're balancing. And then once you've completed, verify that it's balanced by counting everything up, and then just keep repeating your steps until you get to that balanced equation. Let's practice balancing. Okay, so I've got two chemical equations, and we're going to do each one separately. So the first thing we want to do is list out all of our elements, keeping our polyatomics together. Neither one of these have polyatomics, so it's nothing we have to worry about for this particular one. But we have hydrogen, we have chlorine, we have manganese, and we have oxygen. We're going to have the same elements on the other side. We'll just write them in the same order. Next, we total up how much of each we have. We have 1 hydrogen, 1 chlorine, 1 manganese, and 2 oxygens. On the right side, we have 2 hydrogens, 4 chlorines, 1 manganese, and 1 oxygen. So we're going to balance out manganese first because it's our metal. Then we have no polyatomics, so we don't have to worry about that. Go with our non-metal. First is chlorine, then oxygen, then hydrogen. So looking at our chlorine, there are 4 on the right side and only 1 on the left side. So we're going to go ahead and put a 4 here. That'll change this to a 4 and this to a 4. After that, we're going to move on to our oxygen by placing a 2 right here. That changes that to a 2 and changes that to a 4, very conveniently. And that's us balanced. Whew. Let's try the next one. So let's list out our atoms. So we have sodium, oxygen, hydrogen on both sides. We have 1 sodium, 1 oxygen, 2 hydrogens, 1 sodium, 1 oxygen, 3 hydrogens. So let's go ahead and balance this out. Again, our metal, where we start, is good. Our oxygen is good. We're going to start with our hydrogen. So there's no way to take the 2 on the left to make it a 3. So we're going to go ahead and put a 2 here, which will take that to a 4, and that to a 2. And then we could put a 2 here, which will change that to a 4, and a 2 here, changing that to a 2. But that also change that. Okay, so let's see what we're going to do. Start out with sodium. Sodium's good. Oxygen's good. Hydrogen is unbalanced. Now, we see on our right side we have an odd number. On our left side we have an even number. So usually what I'll do is I'll first even it out. So I'll add a 2 right there to even out those hydrogens, giving me a 4 right there. That'll also change this to a 2 and this to a 2. Next, we need to go back up to our list to our metal because we've unbalanced that. By putting a 2 there, we balance that out. And then we need to go to our oxygen. By adding a 2 there, we balance that out. And as a consequence, we also balance that out. So we are good. Let's try a little bit more practice. Okay, so here we've got vanadium, oxygen, hydrogen. So we've got 2, 5, and 2, 2, 4, and 2. So let's start with our vanadium. Our vanadium's 2 on both sides, so we're good there. Oxygen, we have 5 on our left side, 4 on our right side. So we're going to go through and add a 2 here. That gives us 5 and 4. And then we look over. We now need to fix our hydrogens by adding a 2 here. That has balanced this out. Good times. Next is this one. Now, hopefully the first thing you guys recognize is that we have polyatomics. And as I said, we keep our polyatomics together unless the only time we don't keep them together is if they're not on both sides. But if you see a polyatomic on both sides of the equation, keep those polyatomics together. So we're going to balance this as sodium first, then sulfate, nitrate, and lastly hydrogen. So we do not include an oxygen row here because both of the oxygen, or all of the oxygens rather, are with all of the oxygens are with sulfate or nitrate. So we don't need to have our own oxygen area. We do not have any oxygens outside of the sulfate and nitrate. So do not write oxygen in here. Okay, we have 1 sodium, 1 sulfate, 1 nitrate, 2 hydrogens. On the left side, we have 2 sodiums, 1 sulfate, 1 nitrate, and 1 hydrogen. Let's go through. Sodium first, put a 2 here. And then after that, our sulfate is good. Our nitrate, we need to add 2 here. And that balances us out. Quick and easy by keeping those polyatomics together. Okay, what happens if we have a written out equation? The first thing we need to do is we need to go ahead and write out our chemical equation itself. So you must know how to go from our chemical formula. You must know how to go from a name to a chemical formula. So we've got carbon tetrahydride gas, or methane. So that's CH4. And it's a gas. So we're going to put a G in there. It's going to react with water vapor. So water, H2O, and vapor, that means it's a gas. To produce, that means we have an arrow. Carbon monoxide, 1 carbon, 1 oxygen, gas form, and hydrogen gas. So hydrogen gas, that is one of our diatomics. So when I said you needed to memorize those diatomics, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. When I say hydrogen gas, you should know H2O. If I say oxygen gas, you should know O2. Chlorine gas, Cl2. Okay, enough of that. Let's go ahead and balance this out. So we balance it carbon, then oxygen, then hydrogen. So we'll write it in that order. We have 1 carbon, 1 oxygen, 6 hydrogens, 1 carbon, 1 oxygen, 2 hydrogens. Okay, so we're going to want to go ahead. Carbon's good. Oxygen is good. So we're going to add a 3 here. That'll get us to a 6. And we're balanced. quick and easy. Okay, one more example of this. We have solid sodium nitrate decomposing to form solid sodium nitrite and oxygen gas. So make sure you work on that naming. So solid sodium nitrate, Na, NO3 in the solid form, decomposes. That is a type of reaction that we're going to go over, but that means that we're going to our products because it says to form solid sodium nitrite, NO2, and oxygen gas, another one of our diatomics. So just to kind of reiterate, sodium we know is +1, nitrate is -1. They're 1 to 1 because they have the same equal but opposite charges. Nitrite, same idea. It just has a 2 instead of a 3, but it's 1 to 1, so it forms nitrite. Like so. Okay, let's balance this out. Sodium would be first. Now, recognize, please, that we have nitrate on the left side, nitrite on the right side, so we have to break apart our nitrogens and our oxygens. So we're going to have nitrogen and oxygen separate in this particular case. So as long as you have the polyatomics the same on both sides, you can balance them together. If they break apart, decompose in this particular case, then we can't. Okay, so our sodium, we have 1 on both sides, nitrogen 1 on both sides, and then oxygen, there are 3 over here, there are 4 over here. So let's do it. Sodium's good, nitrogen's good. Start with our oxygen. So we're going to have to add a 2 here. That'll bring us to a 6, a 2, and a 2. Then we'll put a 2 here, 2, 2, 6. Okay, one more example. We have solid iron 3 oxide, so iron 3 and oxygen. We combine those. Remember that goes here, that goes here. So we have Fe2O3. And solid carbon, this is not a polyatomic, so it's just as a C. Iron metal, Fe, carbon dioxide, carbon O2. Let's put in our states. We have solid iron oxide, Fe2O3, reacting with solid carbon, Cs, to produce iron metal, Fe, solid, and carbon dioxide gas, CO2 gas. So we have iron, carbon, and oxygen. 2, 1, 3, 1, 1, 2. Start out with our irons, put a 2 here. That gives us a 2 there. Then we mess with our oxygens. We have 3 oxygens here, 2 on the left side. So I'm first going to put a 2 here. And then change this to a 4. And then I'll go through. Don't need to mess with our carbon yet, but my oxygen, I need to put a 3 here, which will give me a 6 here. And then a 3 here gives me a 3, 3. And we are good. Okay, let's move to looking at what type of reactions we have. So when I say things like it decomposes, you'll know what I mean. So we have several different reaction types. Let's look first at combination and decomposition. Combination is A plus B, AB, and decomposition is AB breaks down to produce A plus B. Pretty simple. A combination is going to be 2 or more substances combining to form one product. And then our decomposition is going to be the opposite. One reactant decomposing or breaking down into two or more products. These are probably the easiest ones to recognize, but combination example of this would be 2H2 gas plus O2 gas yields 2H2O gas, or 2Mg solid plus O2 gas goes to 2MgO solid. Decomposition, I need a little more room. So these are my combination. Decomposition. Two HgSCN 2 goes to 2Hg mercury sulfide plus carbon disulfide plus C3N4, or something like this. C3N4 goes to 3CN2 plus N2. And actually this reaction right here, it's called the Pharaoh snake, and if you look in the PowerPoint, I've got a video of this decomposition process. It's kind of cool. Okay, next, combustion reaction. So, rapid reaction that produces a flame. Okay, so the general formula is some hydrocarbon is going to react with oxygen gas to produce carbon dioxide and water. There can be heteroatoms within our hydrocarbon. Some common heteroatoms include oxygen, nitrogen, and sulfur. So it could be a hydrocarbon or a hydrocarbon with heteroatoms. As long as you're reacting it with oxygen, producing carbon dioxide and water, there can be additional things. For instance, if we have ethanol, C2H5OH, so this has a heteroatom, it'll react with oxygen gas to produce carbon dioxide and water. We don't produce anything else if our heteroatom is oxygen. So if our heteroatom is oxygen, no other products are produced. It's just carbon dioxide and water. We can also have a nitrogen-containing species, like this. But it's going to still react the same way. It's going to react with oxygen gas to produce carbon dioxide, water. But now, since we have that nitrogen, it's going to also produce nitrogen dioxide. Okay, so if we have nitrogen in there, we will produce nitrogen dioxide. Okay. And then lastly, if we have sulfur, a sulfur-containing compound, such as this one, it will still react with oxygen gas. It'll still produce carbon dioxide and water. But now it'll also produce sulfur dioxide. So if we've got sulfur in there, we'll produce sulfur dioxide. Okay. Next is a redox reaction or oxidation reduction reaction. So with this one, we have a transfer of electrons from one substance to another. So it involves the transfer of electrons. And we're going to go much more into this one. We're going to have a whole portion of a unit about redox reactions. Generally, they're going to involve metals and metal salts. But not always. But it's usually, again, not always, but a lot of times it'll look like this. We have AB combining to produce A plus and B minus because of that transfer of electrons. Or you might see a metal reacting with a metal salt to produce a new metal salt and a new metal. So we'll transfer one to the other, and this is what we call a single replacement reaction. But not all redox reactions are. This is just an example of a single replacement reaction, which is very common within redox. So for instance, this one right here, iron oxide, iron 3 oxide, reacts with aluminum solid, and we produce a new metal salt, aluminum oxide, and a new metal, iron. So that would be an example of a single replacement redox reaction. We can also see them as combination reactions, such as the rusting of iron. So we have iron solid reacting with atmospheric oxygen to produce iron 3 oxide. Okay. So an example of a single replacement, also an example of a combination, but they don't necessarily have to be either. They can also take on the form of a regular synthesis reaction. So silver reacts with hydrogen sulfide to produce, and oxygen gas to produce silver sulfide and water. So that's another example, and you can know that is a redox reaction by going from a metal to a metal salt. So that's really the only way that you can recognize this particular one. Next is a precipitation reaction. This is a double replacement reaction or metathesis reaction. So all of these will be double replacement or metathesis reactions. There are other double replacement or metathesis reactions. Precipitation is just an example of a double replacement reaction or metathesis reaction. So here we have two substances in the aqueous state combining to produce a substance in the solid state. Aqueous salts combine to form an insoluble salt, and usually a new soluble aqueous salt. Okay. These are going to involve metal salts with polyatomics usually. So usually salts with polyatomics. Although not always, but generally. So we're going to have the general formula AB, AQ plus CD, AQ goes to AC solid plus BD, AQ. Some examples, cadmium sulfate plus potassium sulfide combine to produce cadmium sulfide solid and potassium sulfate in the aqueous state. Another example, iron nitrate, iron 3 nitrate, reacts with sodium hydroxide to produce iron 3 oxide in the solid state plus sodium nitrate. Please note that there is no transfer of electrons in here like we saw with the redox reaction. We're just what we consider switching partners. So that's basically all that's happening here. Last reaction I want to look at is an acid-base neutralization reaction. So we have an acid reacting with a base to produce a neutral substance, a salt and water. Acid reacts with a base, and both are neutralized. So it forms a salt, which a salt is a product of an acid-base neutralization reaction. That's how it's defined. And water. Okay, so we're going to have HA, this is our acid, reacting with BOH, our base, to produce Ba, our salt, and water. So acid, base, salt. And I feel like I don't need to put water on the other one, but just in case, water. Some examples, HCl, hydrochloric acid, reacts with sodium hydroxide to produce sodium chloride and water. Okay. Another example, acetic acid. Reacts with sodium hydroxide to produce. We get a funny arrow here, and we'll talk about why. It's the equilibrium. We'll talk about it in a following unit. But it produces sodium acetate and water. Okay, that is everything. I will talk to you guys in the next one. Bye, guys.